Welcome to Brain Vision.
In the first item, we have to calculate and check if psi 1, 2, and 3 are solutions of the time-dependent Schrodinger's equation or not. We begin by checking psi 1. So, what is the time derivative of psi 1? du psi over dt. Dt is equals to a, which is a constant. The derivative of the exponential is itself, times the derivative of the argument of the exponential. So it multiplies the time derivative of I times k times x minus a times t. But note that the first term, k times x, do not have a t dependence. So it will not contribute to that time derivative. So we will only have minus I times a times the derivative of t with respect to t, which is equals to 1. Then this is equals to minus I times a times psi again. Now, what is the derivative of psi 1 with respect to x? This is equals to a, again, times the exponential, because the derivative of the exponential is itself, times the derivative of the argument of the exponential with respect to x. The derivative of the argument of the exponential with respect to x is equals to I times k times the derivative of x with respect to x, which is 1. This term will not give a contribution since it doesn't depend on x. Therefore, we have this times I times k, and that's it. So this is equals to I times k times psi 1. So, as we can see, the time derivative is the same thing as multiplying by minus I times a, while the spatial derivative is the same thing as multiplying by I times k. Therefore, we can plug in these results in the time-dependent Schrodinger's equation to check if it is satisfied. So we have minus h bar squared divided by 2m times. We will apply the spatial derivative 2 times. So we have minus, not minus, we have I times k squared times psi 1. Because by applying the derivative once, we get a factor of I times k, and by applying the derivative again, we get another factor of I times k, which amounts to I times k squared, plus alpha, which is the constant value for the potential, times psi 1, and this is equals to, should be, I times h times the time derivative of psi 1. Then we have minus I times a times psi 1. Now, we can elaborate this expression that we have minus h bar squared times k squared. Note that we have an I squared here, which gives an extra factor of minus 1, cancelling out this signal. This is divided by 2 times m and multiplies psi 1, plus alpha times psi 1 is equals to h times h bar times a times psi 1. Therefore, we have h bar squared times k squared divided by 2m plus alpha times psi 1 being equals to h bar times a times psi 1. So, is this equation satisfied? Well, yes, it is, if and only if the following condition is also satisfied. So, if this condition is satisfied, then psi 1 is a solution. Now, let us check psi 2. For psi 2, the time derivative is given by the following. d psi 2 dt is equals to a times the derivative of the cosine. The derivative of the cosine is minus sine. K times x minus omega times t. Now we have to multiply it by the derivative of the argument of that cosine, the derivative with respect to t. Then we get a factor of minus omega coming from that derivative. And this is equals to, well, it is equals to minus with minus plus, so a times omega times the sine of k times x minus omega times t. This is the time derivative of psi 2 with respect to time. Now, for the spatial derivative, we have the following. The spatial derivative is again very similar, a times minus sine of k times x minus omega times t times the derivative of the argument of that sine with respect to x, and this gives us an extra factor of k. So we have this times k. And then this is equals to a times k times sine of k times x minus omega times t, with a minus sign in front ahead of it. Now we have to actually calculate the second derivative, as it's not trivial to see what is the value of the second derivative only by looking at this expression. So for the second derivative, we have minus a, which is a constant, times k, which is a constant, times the derivative of sine is cosine, so we have cosine of k times x minus omega times t, times the spatial derivative. And the spatial derivative of the argument gives us an extra factor of k again. Then the second derivative of psi 2 is equals to minus k squared times a times the cosine of k times x minus omega times t. So this is it. Now we have to substitute it in Schrodinger's equation and check if it's satisfied. Schrodinger's equation says that minus h bar squared divided by 2m times the second derivative, which is minus k squared times a times the cosine of k times x minus omega times t, plus the potential times psi 2. Psi 2 is equals to a times the cosine of k times x minus omega times t times a times the cosine of k times x minus omega times t, and this should be equals to I h bar times the I h bar times the time derivative, and the time derivative is given by a times omega times sine of k times x minus omega times t. Then we can work this equation a little to get the following. H bar squared times k squared divided by 2m. Note that this minus sign cancels out this minus sign, plus alpha times a times the cosine of k times x minus omega times t is equals to I h bar omega times a times the sine of k times x minus omega times t. The a's simplify out and we get the following. This quantity times the cosine of k times x minus omega times t should be equals to I times h bar times omega times the sine of k times x minus omega times t. And well, for a particular set of values of x and t, so these only have a solution, actually these have a solution for a particular pair of values for x and t. So it's not true that this equality is satisfied for all x and t. Therefore, we conclude that the wave function psi2 doesn't satisfy Schrodinger's equations for all values of x and t, as it would be expected for an actual solution of that equation. Therefore, we can rule out psi2 as a possible solution. So, psi2 is not a solution. Note that psi1 is actually a solution for any given value of x and t. We have just psi1, and a bunch of constants here and here. So there is no constraints on the values of x and t. Because of that, psi1 is a solution. Now, let us check psi3. The time derivative of psi3 is given by, well, psi3 is a times sine times kx minus omega t. Therefore, the time derivative is given by a times the cosine, which is the derivative of sine of k times x minus omega times t, times the time derivative of the argument of the cosine, which gives us an extra factor of minus omega. Therefore, we have minus omega times a times the cosine of k times x minus omega times t. The spatial derivative is actually very similar to the time derivative, again, because psi3 is very similar to psi2, so we can expect the same kind of calculations. So the derivative of psi3 with respect to the position x is given by the following. This is a times the cosine again, but now we derive the argument of the cosine with respect to x, so this gives us an extra factor of k, and this is equals to k times a times the cosine of k times x minus omega times t. Again, the second derivative isn't trivial when we are working with the coordinate x. Therefore, we have to manually calculate it. So, the second derivative of psi3 with respect to x is equals to k times a times the sine, actually minus sine, which is the derivative of the cosine of k times x minus omega times t, times the derivative of the argument of the sine with respect to x, which gives us an extra factor of k. Then, it is equals to minus k squared times a times the sine of k times x minus omega times t. Then, we plug in Schrodinger's equation and check if this equation is satisfied for any values of x and t. Schrodinger's equation says that minus h bar squared divided by 2m times the second spatial derivative, so minus k squared times a times sine of kx minus omega t plus alpha times the actual wave function, which is a times the sine of kx minus omega t, should be equals to I times h bar times the time derivative, which is minus omega times a times the cosine of k times x minus omega times t. Now we can work out a little bit this equation to get h bar squared k squared divided by 2m. This minus sign cancels out this minus sign, plus alpha times a times sine of kx minus omega t is equals to minus I h bar omega times a times the cosine of kx minus omega t. Again, these constants cancel out, the normalization constants, and we have h bar squared k squared divided by 2m plus alpha times the sine of k times x minus omega times t should be equal to minus I h bar omega times the cosine of k times x minus omega times t. Again, we have the sine of something being equals to the cosine of something else. So, in order to the sine be equal to the cosine, we have to solve them this equation for a particular value of x and t. Therefore, this equality is not satisfied for all values of x and t. There is no choice of alpha and a, for instance, we can do such that this equation is always satisfied. Therefore, psi3 is also not a valid wave function. So we are only left with psi1, which I will write again so we can remember it. Psi1 is equals to a times e to the minus ekx minus at. So we have a to I k times x minus a times t. So this is our only valid solution of the time-dependent Schrodinger's equation. Now remember, psi1 is a solution if and only if another equality is satisfied. It is a solution if and only if this is true. So it is a solution if and only if h bar squared k squared divided by 2m plus alpha is equals to h bar times a. Now, we have to show that this solution satisfies the conservation of energy only if the de Broglie relations hold. The de Broglie relations are the following. Lambda is equals to h divided by the momentum, and a is equals to e divided by h bar. Conservation of energy tells us that E is equals to the kinetic energy plus the potential energy. In our situation, the kinetic energy is equals to p squared divided by 2m, the momentum squared, divided by 2 times the mass, plus alpha, which is the potential for this situation. Now, we can use the first de Broglie relation to write the momentum as p equals to h divided by lambda. And now remember that 1 divided by lambda is equals to k divided by 2 pi, where k is the wave number. Therefore, substituting this 1 over lambda in this equation, we get p is equals to h times k divided by 2 pi, but h divided by 2 pi is h bar, so p is equals to h bar times k. Substituting this result in our equation for the conservation of energy, we get the following. By doing that, we get that E is equals to h bar squared k squared divided by 2 times the mass plus alpha. So, by identifying this term with this term of our solution, we conclude that E is equals to h bar times a. So, A is equals to E divided by h bar, just like the de Broglie relation claimed.